Swayam Prabha. Digital India. Educated India.
Alright, so the next thing that I want to discuss today is actually something that we had in the homework problem, but since we decided to discuss these problems in class, I thought this is a good time to discuss this particular problem. Okay, so this is the problem. So once again I am given oracle access to this function f. At this time it's a n bit input and single bit output function, and the promise that I have is that f of x is x inner product s mod 2. Okay, and this is true for all x. So for every x the function output is x inner product s mod 2. Now in general, classically, how many queries do I need? N, right? Because what we saw also in Simon's, I mean this is just trivial algebra, that I mean I need n linearly independent vectors x. I am querying the function, right? So I can just choose the basis vectors, for example, and I can recover s. Okay, so obviously we want to do better than that. So here quantumly we will use one query. Okay, so classically we need n queries, and quantumly we will make do simply with one query. So now this time I would like you all to think about how to do this. Yeah, so I can give you a hint that indeed proceeding as in Deutsch-Jozsa is the right direction, but it's not, obviously it's not the same problem. So how are you going to use those ideas to solve this problem? Yes, good. So he has the answer. So if I measure in the end after Deutsch-Jozsa, the probability that the amplitude of the point S itself is 1. This is correct. So basically all I have to do is measure, okay, and I am going to get S. So this is how just in one query I can solve and recover S exactly. So let us look at the solution now. So first let me recap the algorithm. Okay, so as usual we have our oracle function oracle here, UF, CF, whatever you want to call it. Okay, so remember what we were doing. This was our algorithm, right? Everyone remembers this was our algorithm. Okay, so in particular here we had the phase kickback happening, right, because at the bottom the y is going to be a minus. So we are going to end up with f of x encoded in the exponent of minus 1. Okay, so in particular let me skip a couple of steps and remind you what is psi 2. So this is x 0 1 to the n minus 1 to the fx x minus, okay, this is over 2 to the n over 2. Alright, and at this stage we apply the Hadamard on the top n bits. And what do we get? We get psi 3 as summation over x, summation now over z. If you remember, minus 1 to the fx plus xz inner product z minus. This is over 2 to the n. Does everyone agree? Okay. So now we measure. Okay, so we are going to forget about the last n bits and we will measure the measure top n bits. And consider the amplitude on z equal to s itself. Okay, so what do you get? So you get summation over x, okay, minus 1 wait, let us simplify this. So minus 1 x s plus s. Do you agree? So fx is nothing but x inner product s, right, and you are considering the point s, z is equal to s. So this is what you get, correct? This is the coefficient. Now can you tell me what is this term on top? I claim that it is 0. Why? It's mod 2, right, and I got a factor 2 here. So this term is 0. So this means that this is minus 1 to the 0, which means it is 1, and I am summing it 2 to the n times. So that means I get 2 to the n, which will cancel with the denominator and result in 1. Okay. So what was the idea here? Basically the fact that f of x is itself x inner product s, right. The way to think about this algorithm is that I am getting, using the ideas that we have already seen, I can get x inner product s plus x inner product z, right, in the exponent. Yeah. So basically I will get x inner product s plus x inner product z in the exponent. This is the term that I am interested in, right. So this is my interesting term. Okay, so this, of course I can write it as x s plus z, right. So staring at this term gives me the answer, right. So because this is an inner product mod 2, right, when z is equal to s, then obviously I get this inner product to be 0, and then this leads me to a simplification which gives me something. It is also interesting to think about what happens when z is not equal to s. So there the amplitude should become 0, right. So if all my amplitude is going and sitting on the point z equal to s, then that obviously means that for all the rest of the points it's becoming 0. So who can argue that for me? Why is it that the amplitude is 0 for these points? Why is this?
Because the mod is it's mod 2, the other things should be equally likely to happen. Right?
Yes, that's right. So, what he's saying is that basically this is happening mod 2. So, for any fixed s plus z, right, I can now find 2 points exactly which give me opposite answers. Okay, so let's fix some s plus z. It doesn't matter what it is, right? So, without loss of generality, let me think of this as, you know, starting with 1 and then having any characters after that. This is without loss of generality, because if it starts with 0, then, you know, I can just take the first one that occurs. Okay. Now consider some x, you know, let me consider an x0, let us say, right, which is 0 followed by some string, I will call that x prime, and let me consider x1 which is 1 followed by x prime. Okay. Now, what is going to happen is that I can write for every x0, I have an x1 which is going to lead to a plus 1 and a minus 1 correspondingly, right. So, my claim is that basically if I have, right, if I think of minus 1 to the x0 z plus s, right, and I think of a minus 1 to the, you know, x1 z plus s, right, if I think of these. So, in this case, what do I get? So, this is going to be 0, right. So, this will become 1 plus 1, correct. Does everyone agree? This becomes plus 1 because this exponent becomes 0. Why is that? Because, you know, it does not matter. Oh, wait. Yeah, actually maybe I cannot claim that it becomes plus 1. Basically I have, let me write it very explicitly. Okay, so let me consider the inner product. Let me consider this inner product. Okay, so the first bit of x0 is 0, right, and so I get, you know, 0 times 1 plus whatever, some x prime star star star, correct. This is in this case. In this case, right, I get 1 times 1. Everyone agrees? Yeah. So, I get 1 times 1 plus the same inner product, right. Let me call this delta. So, this is 1 plus delta. So, it is not that I can claim that the first one is the first inner product is 0 and the second inner product is 1. I cannot claim that because I do not know what these wildcards are. I do not even know what x prime is. But whatever it is, right, the other one is the opposite of that. And if one of them is 0 and one of them is 1, then that means that downstairs I get a plus 1 and a minus 1, which will cancel each other. So, this is the reason why when z is not equal to s, I end up getting amplitude 0, because all the terms will sort of cancel each other. For every plus 1, there will be a corresponding minus 1 on exactly one other point. By the way, obviously this analysis of what happens when z is not equal to s is in fact not even necessary, right. If I found one point where all the amplitude is, that's that. When I measure it, I will get that point, right. So, it is not that it is even necessary for me to analyze what happens otherwise, but the reason I am doing it is just for us to try and get an intuition. Okay, so in this case, the idea was that when I run Deutsch-Jossa, right, I am going to get this fx plus inner product xz in the exponent, right. My fx has a very particular form. It is itself xs, the inner product of x and s. So, now what should I do? Well, I can write down minus 1 to the inner product of x and s plus z, and I can just play around with it and see, you know, for what values of z what behavior will I get. And a very immediate thing that pops out is, well, the first thing to try is, you know, maybe the first thing to try is zeros. The second thing to try will be, you know, I am trying to find as well what happens at s, right. So you can see very quickly that for that particular point, I am actually going to get all my probability there. So even if I did not start out with the intuition that, you know, all the probability should be concentrated there, I am just trying to think of a problem solving method here, right, that basically when I stare at this, the way for me to think is, well, what are, you know, what are special points I can try. I am trying to make sense of this term that I have, right. So what properties does this have? So let me, you know, try and see if I can understand this behavior by evaluating it at different points. So there, if I evaluate it at 0, I get something. If I evaluate it at s, I get immediately exactly, you know, probability 1. So I'm already done. Okay, so the reason for doing this in class is for us to sort of build our problem solving skills. Like we want to also design quantum algorithms, right. So just seeing them and analyzing them is not enough. We also want to develop ways of designing them, and developing an intuition for what will work, what will not work, this may take us some time. But given that, you know, we know that we are going to use Joyce-Jossa type ideas, then, you know, immediately what we can do is just try out a few things and pretty quickly we get the right answer. Okay, so this is another very nice example of the same paradigm being used, and I am hoping that by now, you know, we have seen a few examples where we can see that basically apart from probabilistic reasoning, which is, you know, also there in randomized algorithms, what we are really using is this input superposition, and then once you evaluate the function and get some kind of output superposition in whichever form, then typically we use the Hadamard to, you know, change the basis and observe that for certain special points, you know, I get useful information about the function. This is what we are doing so far, right. So we have seen by now 3 examples of this. I am counting Deutsch and Joyce-Jossa as one example, right. One is a general case of the other, then there is Simons, and now there is this. So these are basically, once I get the output superposition in some form and I apply the Hadamard, right, what does it do? It changes the, you know, it changes the basis. Right, so it gives me for each point x, it gives me a linear combination of, you know, many different points with different amplitudes, and all that I have done in all of these approaches is to figure out special points at which special behavior is observed and make use of that to solve my problem. Does everyone see that? Okay, so this is why I wanted us to do a little bit of problem solving also in class.